So let us solve this kind of linear system, okay, where you have to find four unknowns, that is x, y, z, and t. Okay. Now let us find that. Okay. Now the given system, let us write in x, y, z, and t form. Okay. Now the given system looks like this. Now, first, let us call this as delta. Okay, the corresponding is x is 1, and y 1, minus 3, and minus 4, and so on. Let us write the rest of them. Okay, so you get this. Now we'll do the row operations. So let us do the row operations R2, so that this will be R2 minus 2R1, okay, and R3, that will be R3 minus 2. So therefore get as which is 1 minus 3 minus 4, this is 0, minus 1 11 9, and 0 0 8 5, and 0 3 7 13. Okay, so we get this. Okay, after applying this. Okay, and since this again can be written as, so that will be minus 1, okay, 11 9 0 8 5
5,
3
3,
7 13. Okay,
7.
so we got this. Now let us find the determinant of this. So this will be minus 1 2 yeah. So after that we get the determinant of this, so that will be minus 1 into 8 into 40 minus 5 into 40, right? And which will result to minus 120, which is not equal to 0. Okay, now by Kramer's rule, we have x as delta 1, okay, by delta, and y delta 2 by delta, and z as delta 3 by delta, and t delta 4 by delta. Okay. Okay. Likewise, you can find with respect to y, which is delta of t delta, which is 1 by 120, which is 1, 2, 3, and minus 1, 5, 8, 3, 5, 2, and minus 2, minus 4, 1, minus 3, which results to minus 24 by minus 3, which is equal to 1 by 5. So you get x value, y value, and z value, and t value. Okay, which is x is equal to 2, y is 1 by 5, and z is 0, and t is 4 by 5. Okay. Let us find it. Now, the characteristic equation of A is given by, that is, A minus lambda I, which is equal to 0. Okay, so this will be 1, 4, 3, 2, okay, minus lambda I is 1, 0, 0, 1, okay, which is equal to 0. So let us that. So that would be 1 minus lambda, okay, and 4, 3, 2 minus lambda, which is equal to 0. Okay. Now let us find the determinant of this. So that would be, take this as lambda plus 2 and lambda minus 5 is 0. Okay. So we now what we got as lambda plus 2 and lambda minus 5 is equal to 0. Okay. Now this lambda has got two values, that is minus 2 and 5. These are the eigen values. These are the eigenvalues. Now let us find what are the eigenvectors of this. Okay, so now let us take lambda as minus 2. So this will be a minus lambda I into x is 0. Okay, so that will be minus 2. So that will be a minus 2 into I into x is equal to 0. Okay, so let us substitute it. So this will be 1 plus 2 and 4 and 3, 2 plus 2, and corresponding to that will be x1, x2, which is equal to 0, 0. So we get this as 3x1 plus 4x2, which is equal to 0. Let us consider as x2 as k. So x1 will be minus 4k by 3. Okay. So So the for a lambda which is -2, we get as
-1.
-4/3 and 1. Okay. Yeah. So these are the corresponding eigenvectors. Eigenvectors. Okay. Now we have again another value which is lambda as 5, right?
Okay.
So when you substitute it, so a minus 5i, okay, into x is equal to 0, right? So get that as -4, 4, 3, -3, and x1, x2, and 0, 0. So the corresponding you'll get as -4x1 plus 4x2 is equal to 0. Okay, and yeah, or -x1 plus x2 is equal to 0, or you'll get x, if you take x2 as k, and you'll get x1 as k. Okay, so for lambda which is 5, you get the eigenvalue 1 and 1, okay, which is the eigenvalue. Okay. That's what we'll find, verify the Cayley-Hamilton theorem, right? And okay, let's solve this. Now the characteristic equation of A will be A minus lambda I is equal to 0. Okay, so let us put that. So that would be 2 minus lambda 1, 2, and 5, 3 minus lambda 3 minus 1, 0 minus 2 minus lambda, which is equal to 0. Now this will be 2 minus lambda, right? This is 3 minus lambda, 2 minus 2 minus lambda, 0, correct? Minus 1, or you can consider as minus 5. Okay, and let us take the row. You get minus 2 minus lambda minus 1, okay, and we get that as 3 minus 6 plus 2 lambda, which is equal to 0. Okay. So further simplifying it, so after simplifying we get this. Okay. Now to prove that A satisfies lambda cube minus 3 lambda square minus 3 lambda minus 1, the character equation of A square. Okay, so get a square. So therefore we get a square. Now to find a cube, which is a square into a. So a square we already got it. So 7, 5, 3, 22, 14, 13, 0 minus 1, 2. So this is multiplied into 2, 1, 2, 5, 3, 3, minus 1, 0, minus 2. Okay. So we got a cube. Now let us put a cube, a square, and a in that. Okay, and 1 is nothing but I. Okay? Let us put that. So we had got this. So a cube minus 3a square minus 7a minus I. Okay, so this result should be equal to 0. Okay, yeah. So a cube, which is 36, 22, 23, 101, 64, 60, minus 7, minus 3, minus 7, right? And this will be minus when I multiply it. So I'll get plus, okay, plus 21, minus 21. I'll take minus inside. Okay, and minus 15, minus 9, and minus 66, minus 42, minus 39, and 0, 3, minus 6. Okay, and we have one more term, plus, keep it outside, minus 14, minus 7, minus 14, and minus 35, minus 21, minus 21, minus 7, 0, and 14. Okay, and plus I'll take it outside, and we'll have minus 1, 0, 0, 0, minus 1, 0, 0, 0, minus 1. Okay. This is I. Now let us compute it. So this will be equal to 0, 0, 0, 0, 0, 0, 0, 0, 0. So therefore A satisfies its characteristic equation. Okay, so hence we have verified Cayley-Hamilton's theorem. Okay,